Okay, good evening. In the last class, we had seen the dynamic braking of three-phase induction motor. In fact, we started with regenerative braking. We took a look at plugging, and then we came over to dynamic braking, and we said that the dynamic braking is different from what happens in a DC motor because the DC motor will have its field excitation separately. So there is nothing like the excitation is completely lost or something in the case of DC machine. Whereas in the case of induction motor, because it's a singly fed machine, the excitation is lost the moment you disconnect the three-phase supply. So there should be some way of giving the excitation from somewhere. So if let us say this is a three-phase induction motor, which is actually being fed from the three-phase supply. So this is the three-phase supply, which is feeding the three-phase induction motor. Now, if we disconnect the three-phase supply, then the stator is going to lose its excitation completely. So we have to provide the excitation probably by connecting the capacitor. So the three-phase capacitor bank being connected to the stator side, that's what we called as capacitor braking. So in dynamic braking, first of all, we talked about capacitor braking. This was done in the last class. Then we said that the excitation can be given by connecting a single phase AC supply. So that we will call as AC dynamic braking. So instead of a three-phase supply, we will be connecting a single phase AC supply to give the excitation that's required from the stator side. We'll just talk about this in detail in a little while. Instead of providing a AC supply, we can also provide a DC supply. So if we are giving a DC supply, we call that as DC dynamic braking. And the fourth type of dynamic braking method we call as zero sequence braking. The zero sequence braking actually refers to connecting a single phase supply or a DC supply to series connected windings or parallel connected windings of the induction motor. All three windings will be connected in parallel. Like for example, if I'm going to have this is one winding, this is the second winding, and this is the third winding. If it is a star connected winding, I can also try to connect all of them together like this and connect a power supply here. It can be a DC current or AC current. So zero sequence braking essentially refers to all the three-phase currents being in phase with each other. They are co-phasal. Or if it is delta connected winding, let us say this is the delta connected winding of the induction motor. I can just disconnect one junction and I can try to connect a single phase source through this. So I can connect an AC source or DC source. So maybe a current will flow like this and all of them are connected in series. So the current will be co-phasal again. So the three-phase currents are co-phasal. That is the reason why we will call that as zero sequence braking. Now let us try to first of all start with AC dynamic braking. So in AC dynamic braking, as the name indicates, we are going to provide an AC supply from the stator side to maintain the excitation. So let us say originally I'm going to have the three-phase power supply somewhat like this. This is, let's say this is A phase. So this is going to be A phase and this is B phase and this is C phase. And the three phases are connected to the three-phase power supply directly. So if I'm going to have the three-phase power supply connected here, it is going to work as a normal three-phase induction motor. So here is the three-phase power supply. Okay. So if I want to implement AC dynamic braking, what I can do is probably just leave out one of the terminals without connecting it. So this is A phase is open circuited Now to B phase and C phase, I'm going to connect a single phase supply. So let us say here is the single phase supply that I am connecting to the stator side of the induction motor. The rotor could be a normal squirrel cage rotor. So I'm showing the rotor here. This is a squirrel cage rotor. The same way I am having the rotor here, which is a squirrel cage rotor. So this power supply, what I have got is single phase. So definitely this machine is going to experience unbalance or imbalance. So this is an unbalanced power supply that is being applied to a three-phase induction motor. So we are going to use symmetrical components for analyzing this induction motor, which is actually experiencing unbalance. Symmetrical component analysis, you guys must have studied in power system. Generally, when you have unsymmetrical fault, like single phase to line fault or double line to ground fault. So those things you will analyze using symmetrical component. So the symmetrical component, the basic principle is somewhat like this. If we try to look at the basic principle of symmetrical component analysis, if there is a three-phase unbalanced system, we are going to have maybe VA angle, say alpha, and VB is going to have an angle beta, and VC is going to have an angle gamma. Normally, if it is all balanced, we will have VA, VB, VC being equal to each other. If I try to look at the magnitude, all of them will be equal to each other. This is the balanced case as far as the magnitude is concerned. The same way, alpha and beta, if I try to look at the difference, that will be 120 degrees. The same way, gamma minus beta, again, I will have 120 degrees as the angle. So in balanced case, if I know just VA angle alpha, I should be able to infer what is VB angle beta and what is VC angle gamma. Everything I would be able to infer. Whereas, if it is an unbalanced case, when I'm talking about unbalanced case, I am going to have basically 6 variables, which are VA, VB, VC, all of them are unknown. The same way alpha, beta, and gamma, everything needs to be defined. Unless I defined all of them, I'm not going to be able to solve for the currents and so on. So this basically has 6 degrees of freedom. This is going to have 6 degrees of freedom. So rather than representing this by independent vectors VA, VB, VC along with the phase angle alpha, beta, and gamma, we can represent this by 3 sets of balanced voltages. So we are going to define this particular unbalanced voltages with 3 sets of balanced voltages, which we call as symmetrical components. One of them is going to be positive sequence voltage. So the positive sequence voltage, if I define that, I should say this is going to be VAP, maybe an angle of alpha 1. So we are going to have VBP, which will also have the same magnitude, same as VAP, but it will be at a phase angle of alpha 1 minus 120 degrees. And we will have VCP, which will be having a phase angle of alpha 1 plus 120 degrees. So I'm going to have 3 vectors somewhat like this. If I may call this as VAP, I'm going to have VBP here and VCP here. So the moment I define VAP along with the phase angle, I should be able to infer immediately what is VBP and what is VCP. So these vectors are going to rotate in this direction, that is anti-clockwise direction. we call that as positive sequence voltage. The second component is negative sequence voltage. And the negative sequence voltage will have again VAN with probably another phase angle which I may call as beta 1. And we are going to have VBN which will have beta 1 plus 120 degrees. Please note that the B phase voltage is leading A phase voltage by 120 degrees in this particular case. The same way I'm going to have VCN. So VCN is going to have beta 1 minus 120 degrees as the phase angle. So this is the way it is going to work. Now, if I try to mention this in the form of phasor, maybe this is VAN, and I'm going to have the two more vectors which are again having the magnitude which is same as that of the magnitude of VAN. So I'm going to have this as VBN and this is going to be VCN. And I'm going to have this is probably at an angle beta 1. Then this is going to be beta 1 plus 120 degrees. And this is going to be beta 1 minus 120 degrees. So this is the negative sequence voltage. The last one, the third component is going to be zero sequence voltage. And zero sequence voltage, all the three voltages, that is VA0, VB0, VC0, all of them are going to be co-phasal. They are going to be in phase with each other. So if I have VA0 as the value VA0 angle, say gamma, I'm going to have VB0 also as VB0 angle gamma, where VA0 and VB0 will be equal to each other. And similarly, VC0 is going to be VC0 angle gamma. So I can represent this somewhat like this. I'm going to have probably this as VA0. Then VB0 will be exactly parallel to this and VC0 will also be parallel to this. All three of them will be parallel to each other. Now what we have done is we have actually divided the original VA, VB, VC which were unbalanced into three components which are symmetrical. The positive sequence component, which is going to have VAP or VBP or VCP as the magnitude, all of them being equal to each other. But that is essentially going to have the rotation in the positive direction, where VA is going to lead VB by 120 degrees and VC is going to lag behind VB by another 120 degrees. Whereas negative sequence component, again, the magnitudes are going to be equal with a specific phase angle. And the direction of rotation in this particular case is going to be the other way around as compared to the positive sequence voltage. Whereas zero sequence voltage, that's not going to rotate at all. All the voltages are going to be co-phasal. A phase, B phase, and C phase voltages are going to be co-phasal. So finally, if I want to write what is VA, so if I want to write originally whatever is VA, that VA, what I have got will be the summation of VA naught plus VAP plus VAN. Of course, I have to include the phase angle as well. So VA naught angle alpha 1, VA naught angle gamma, VAP angle alpha 1 and VAN angle beta 1 and so on. So I have to include them along with the phase angle. The same way I'm going to have VB, which is going to be equal to VB naught plus VAP angle minus 120 degrees because it is actually lagging behind VA corresponding to positive sequence. Similarly, this is going to be VAN angle plus 120 degrees. The same way I can write VC is equal to VC naught plus VAP angle 120 degrees and VAN angle minus 120 degrees. And if I may write some quantity A equal to 1 angle 120 degrees, I can write this as cos 120 plus j sine 120. That will be minus half plus j root 3 by 2. So I can say that a square, which is actually 1 angle 240, that will be same as 1 angle minus 120. So I should be able to write this as again minus half minus j root 3 by 2. Now, if I write this in the form of a matrix equation, if I try to write this in the form of a matrix equation, I should be able to write VA, VB, VC is equal to, first of all, VA naught, VAP, and VAN. This can be multiplied by, first of all, I should say 1, 1, and 1 because VA naught plus VAP plus VAN will give me VA. Then I can write similarly 1, that is VA naught plus VAP angle minus 120. So that is essentially A square and this is A and this is going to be 1A square. So this is what gives me the relationship between the components of the symmetrical components transformation and how that can be transformed into the original unbalanced VA, VB, VC three-phase voltages. So this gives the transformation between the original unbalanced voltages and the symmetrical components which are used to represent this particular unbalanced voltage in an easy manner. Now, whatever we have got here, this particular matrix is an orthogonal matrix. So we should be able to say, if I call this matrix as the transformation matrix T, this is the transformation matrix which is transforming from unbalanced voltages VA, VB, VC into positive sequence, negative sequence, and zero sequence voltages. If I call this as T, so this matrix T is orthogonal in nature. So this is going to have T inverse equal to T transpose conjugate. So if I transpose this matrix and take the conjugate of that, that will automatically give me the inverse. So I should be able to write this particular matrix equation, what I have got, if I may call that as matrix equation 1, I should be able to write the same matrix equation in the reverse direction as VA naught, VAP, and VAN. That is the positive sequence component, negative sequence component, and zero sequence component. I should be able to write this as the matrix which is transpose of this, that is 1, 1, 1. And again, I should have 1 A square A. But if you actually look at A and A square, they are basically conjugate of each other. These two are conjugates of each other. So A's conjugate is A square and A square is conjugate is A. So I should be able to just write this as 1 A square and 1 A square A. This matrix has to be multiplied by VA, VB, and VC, the original unbalanced components, from which I should be able to obtain the zero sequence, positive sequence, and negative sequence voltages directly. Only thing what You have to realize this. Now, if I look at VA, this VA, if I just add VA naught, VAP and VAN, I'm getting VA. There is no doubt about that. But if I try to look at now positive sequence component from here, from this matrix equation, here it is coming out to be VAP is equal to VA plus A times VB plus A square times VC. Okay. Now, if I am going to have only balanced voltage, I will get this to be basically 3 times VA, because 1 plus A times VB will be same as VA and A square times VC will be again same as VA. So I'll get 3 times VA, which is definitely not correct because the positive sequence voltage should be equal to whatever is the original A phase voltage itself. So there should be a 1 by 3 factor coming up here. So it should be 1 by 3 times this. This is the equation that actually transforms the original unbalanced voltages into positive sequence, negative sequence, and zero sequence component. Now that we have established this relationship between the sequence components and the original unbalanced voltage, now let us try to analyze the single phase AC dynamic braking of the three-phase induction motor. So let us try to do the single phase AC dynamic braking analysis. So if you look at it, we drew the circuit diagram somewhat like this. This is A phase, which was left open, and this is B phase, and this is C phase. So we are connecting, instead of connecting a three-phase supply, now what we are connecting is simply a single phase AC voltage. So I'm going to connect a single phase AC voltage. Okay, so this is some voltage, single phase voltage that I have connected. Now, if a current is flowing in this direction, which I may call as some I, it has to return through this direction. So it has to be the same current which is returning back to the single phase supply. So in this particular case, I should be able to say IA equal to 0, IB equal to minus IC, which is probably equal to I. Okay, so this is the way the current relationships are. So if I want to know what is the positive sequence component of current, so let me try to calculate what is IAP or IP as such. Let me say this is positive sequence component of current, this is going to be negative sequence component of current, and this is going to be zero sequence component of current. So the positive sequence component of current comes out to be 1 by 3 times IA plus A times IB plus A square times IC. So IA is 0. This is already written here. And IB and IC are having essentially reversal of sign as compared to each other. So this is going to be 1 by 3 times A minus A square times I. And A is minus half plus J root 3 by 2. And A square is minus half minus J root 3 by 2. So you can say that A minus A square, when you calculate, this half and this half should get cancelled. Only this J and J root 3 by 2. So when I add them, it should be J root 3. So I will have I J times I divided by root 3, because there is root 3 up and root 3 is in the denominator. So this is going to be Ji divided by root 3. Whereas when I calculate In, it is exactly the reverse, because this is going to be 1 by 3 times Ia plus A square times IB plus A times IC. So it is exactly the reverse of this. So that is going to be minus JI divided by root 3. That is going to be the negative sequence current. So the positive sequence current and negative sequence current, both of them happen to be equal to each other in the magnitude, but they are actually reverse in terms of the sign. So we can say that the positive sequence network and negative sequence network are connected in anti-series or series opposition in this particular way. So if we say that, then we should be able to draw the complete network somewhat like this. I should be able to connect probably a voltage, and I should show that this is the positive sequence network, and I should have the negative sequence network somewhat like this. And then I should have ultimately the return current. So this is the forward current and this is the return current. This is the way it is going to be. So this is the negative sequence network. So that means if I call that the voltage drop here as VP with plus here and minus here, and I should have the voltage drop here in the negative sequence network. Again, I should have plus here and minus here. So VP minus VN should be the total voltage applied. This is the way it is going to be connected. So VP minus VN is going to be the total voltage applied to this unsymmetrical network of the stator of the induction motor. Okay, so I can calculate again what is VP. Let us try to again look at what is VP from here. So the positive sequence voltage in this particular case is VA minus VA plus A times VB and A square times VC. Okay, so I should be able to write this as VA plus A times VB plus A square times VC. And this has to be subtracted from VA times A square times VB and A times VC. This is what is the negative sequence voltage. Whatever we wrote here, I'm writing the same thing. Here we wrote it for current, whereas what we are writing here is for voltage. So this VA and this VA will get cancelled, and we can write this as A plus A square, rather AVB and A square. So I should be able to write this as A minus A square times VB minus A square minus A times VC. So if I just say this is also A minus A square, so I should be able to write this as A minus A square or A square minus A. I should be able to write this as again J times VBC divided by root 3. So if I apply a voltage of VBC divided by root 3, I'll get a current of I by root 3. So I can simply say the voltage applied here is VBC. I will get a current of I through this. So I should be able to draw the equivalent circuit somewhat like this. I have to first of all show the equivalent circuit of the induction motor. Whatever we have calculated, please note it is all per phase voltages, because the positive sequence A phase voltage and negative sequence A phase voltage. That's what we have considered. The same way, the current flowing through the phase winding. That's what we have considered. So I should be able to write this as R1 and this is X1, which is the stator of the induction motor. Now, what I have got here should be the positive sequence voltage visualized from the stator side. So this has to be Xm, which is the magnetizing current, magnetizing reactance. Now this will be R2 dash divided by S because it is forward rotating magnetic field, with respect to which we are actually calculating the torque generated in the rotor. The slip will also correspond to the normal definition of the slip as far as the positive sequence component is concerned. And we are going to have this as X2 dash. So this is basically the positive sequence component of the network. Now, when we talk about negative sequence, the magnetizing reactance is going to be still Xm, let us say, because we are doing this with respect to the stator side frequency. Whereas here, if you look at the slip, it is very similar to plug-in case, where I'm going to have a synchronous speed of the revolving magnetic field in this direction, whereas the rotor speed is in the opposite direction. So the two are exactly opposite to each other. So the synchronous speed of the negative sequence component is opposite to that of the positive sequence component. So we will have in this particular case, the denominator component here is going to be 2 minus S, or 2 dash divided by 2 minus S. That is the one which is corresponding to the slip for the negative sequence component. And we will have X2 dash here. Now, this has to be completed now with R1 and X1 on the other side as well, which is corresponding to again negative sequence component, which is at synchronous frequency but revolving in the opposite direction. Okay, so what we apply here as the voltage is, let us say VBC, or the single phase voltage, and this is going to be the positive sequence component network, whereas this is going to be the negative sequence component network. Now we should be able to calculate the torque, which is corresponding to the positive sequence component, which will be I2 square R2 dash by S, omega S. And this will be I2 square R2 dash divided by 2 minus S and omega S. So this is going to be definitely much lower in terms of the torque developed, that is the braking torque, whereas this is going to be the motoring torque. So if I try to draw the torque speed characteristics corresponding to this, so this is going to be the original motoring characteristics for the induction motor. And if I try to draw for the plugging characteristics, that is going to be somewhat like this. This is going to be the plugging characteristics, what I get for the induction motor. Now, original operating point might have been somewhere here. So under this condition, if under this speed, if I try to suddenly disconnect the motor from the three-phase supply and connect it to a single-phase supply, whatever is the torque that is depicted by the induction motor, so this is actually our speed and this is going to be the torque. So it will be the difference between whatever is the motoring torque and braking torque. And the braking torque is really, really small because 2 minus S factor is coming into picture when you calculate the braking torque. So it's not going to be much. So if I try to increase the rotor resistance, by chance, if I am talking about this for a wound rotor induction motor, and if I try to increase the rotor resistance quite a bit, then I may get a good amount of braking torque here, whereas the motoring torque is going to be smaller. So the AC dynamic braking will also work very well, and it will be able to generate a good amount of braking torque only if we play around with the rotor resistance. If we don't play around with the rotor resistance, we are not going to be able to get a good amount of braking torque. So the braking performance will not be good for a cage induction motor. So the bottom line is for a cage induction motor, AC dynamic braking cannot work very well or cannot yield a good performance. So it's not going to be really all that great. Okay. So in general, AC dynamic braking works much better for for a wound rotor induction motor rather than a squirrel cage induction motor. Okay. So let us try to now take a look at the performance of an induction motor for DC dynamic braking. So let us try to see how well the induction motor will, perform for a DC dynamic braking case. So what do we do in DC dynamic braking? In DC dynamic braking, again, if I'm going to have this as the stator terminal, this is A, this is B phase, and this is C phase. And let's say they were connected to the three-phase supply when the machine was working as a motor, normal motor. When I want this to work as a brake, or if I want to brake the induction motor and bring it to a standstill condition, let us say this is B phase and this is C phase. A phase, I'm leaving it open, and B phase and C phase, I'm going to connect it to a DC supply. So qualitatively, if I try to look at it, I am looking at a stationary magnetic field. So let us say this is omega m, and this is going to be the torque. And originally, the characteristics of the induction motor was somewhat like this. This is what is the original characteristics of the induction motor. So I'm going to have the original characteristic of the induction motor somewhat like this. Now, if I'm talking about DC being applied to the stator side, the synchronous speed is supposed to be 0. So I should translate the same characteristic somewhat like this. This is how I should translate it. So if I take it to the other side, I should take the characteristic somewhat like this. This is how the characteristic should be taken to the regenerative side of DC dynamic braking. So if the original operating point had been here, from here I would have got a good amount of braking torque. There is no doubt. But it is in steady state, unstable region of operation of the speed torque characteristics. So that is definitely not a good operating point as far as a squirrel cage induction motor is concerned. So if I want a good amount of braking torque and still I want to get a good braking performance with the DC supply being applied, then I should see as though a huge amount of rotor resistance is included so that I get a good amount of braking torque even here. So this will still be in stable region of operation. So even for DC dynamic braking, although the braking torque originally developed is good, because it is in the unstable region of operation of the induction motor. So this portion is unstable region of operation. So this is unstable region. Whereas this is the stable region as far as the induction motor operation is concerned. So I'm going to have this as the stable region. So I want to have the stable region somewhat extended. That's why we are including higher R2 if I am able to include a higher rotor resistance, then I'll be able to get a good braking performance even for DC dynamic braking. The braking torque will be quite large and it will still belong to stable region. So again, DC dynamic braking also works better for wound rotor induction motor. Wound rotor induction motor. So to analyze this somewhat with equations and things like that, the first and foremost thing what you have to realize is the stator revolving magnetic field originally was omega s, and the rotor revolving magnetic or rotor was rotating at a speed of omega r, and the difference between these two was the slip speed. So this is the slip speed. So we can call this as S times omega s, because slip is omega s minus omega r divided by omega s. So we can say uh, uh, S times omega s is going to be omega s minus omega r, which is the slip speed. So the induced EMF in the rotor circuit had basically a frequency which is corresponding to S times F1, where F1 is the frequency of the stator supply itself, right? So if we are looking at uh, what will be the case once DC dynamic braking. So once the DC dynamic braking is incorporated, I am going to have omega s equal to 0. There is no omega s, but omega r is basically rotating at the same speed, because as the rotor is rotating at omega r, at that point itself, suddenly the three-phase supply has been disconnected from the stator side and DC supply has been connected. Now, the rotor conductors are going to look at the stator magnetic field, which is stationary. When it looks at that, it is going to see a relative speed of omega r. So that is going to be actually 0 minus omega r. So that is going to be minus omega r itself. So you are going to see a speed of omega r, but it is in the opposite sense of the original direction of rotation of the rotor. So we are going to have the slip to be actually 1 minus s now, which is actually capital S. That is original slip. If it had been slip s, small s, now the relative velocity between the revolving magnetic field of the stator, which is actually 0 in this particular case. So this is going to be 0. And now 0 minus omega r, we are going to have the relative speed corresponding to omega r itself. So the slip in this particular case is capital S, which is very large. Previously, if it had been small s had been 2%, now capital S is going to be 98%. It is going to be really, really big. So if I try to look at the rotor side induced EMF, I am going to have, this is going to be the rotor side induced EMF, which is very high. And I'm going to have R2 dash as R2 as the rotor side resistance. And I'm going to have X2 as the rotor side, S times X2 as the rotor side reactance. S is very large. The frequency of the induced EMF of the rotor is very large. So this is the rotor equivalent circuit. But if I try to again divide it by capital S, I'm going to have this as E2, which is the standstill induced EMF originally for the rotor. And I'm going to have R2 divided by capital S, and I'm going to have X2 as the rotor reactance, and this is going to be the rotor equivalent circuit right now when I am incorporating DC dynamic braking in this particular machine. So this is basically the rotor equivalent circuit during DC dynamic braking. If I try to look at the stator equivalent circuit, I have to first of all check I have A phase completely opened up and I have B phase and C phase here. So this is B phase and C phase, and I have connected a DC source here. So I'm going to have a current maybe I flowing here, and this will also be the return current I. And if I assume that each phase of this machine is having n number of turns, now the resultant MMF, what I see in the air gap, that is going to be as per cosine law. I'm going to have whatever is FB whole square, that is the MMF of B phase, and FC whole square plus 2 FB and cosine of the angle between FB and FC. Okay. And I have to take the square root of this. This is going to be the resultant MMF. So I can write this as n times I the whole square plus minus n times I, because the current is minus I for the C phase, which is exactly opposite to that of B phase current. So this is minus n times I the whole square, plus I'm going to have 2 times Ni multiplied by minus Ni, and I'm going to have cos of 120 because the angle between these two is 120 degrees. So this entire thing, whatever I have got here, I have to take the square root of this. Square root of this. Okay, so let me write, this is the square root of this particular thing. Okay. Now, if I calculate this, I will have n square I square, n square I square, and this is also going to be another n square I square. So I will have this is equal to, when I write this, this should be equal to √3 of ni. When I take the square root, I should have this to be √3 times ni. That's it. That is going to be the overall MMF. Now, this √3 times Ni, this MMF is actually giving rise to a stationary magnetic field, but this is being visualized by the rotor conductors as though it is rotating at a speed which is corresponding to omega r in the reverse direction. That's what we said. So, if such a revolving magnetic field has to be created, if this revolving magnetic field has to be created by a three-phase current. If this revolving magnetic field has to be created by a three-phase current, then what should be the RMS value per phase? If I try to calculate that, if you may recall, the three-phase revolving magnetic field theory says 3/2 times whatever is the peak value of phase current, right? Multiplied by the number of turns. That is what is the strength of the MMF or resultant strength of the MMF. So I should be able to write this as 3/2 times √2 times I phase RMS. So let me write this as 3 by root 2 multiplied by IS, where this is the per phase RMS current multiplied by N. Okay, so if I want to create a revolving magnetic field of strength this much by a DC current, so this is the DC current, then I should be able to calculate the AC current, which will actually create a similar strength, a similar magnetic field of equal strength. So I should be able to write this as root 3 times N times IDC equal to 3 divided by root 2 times IS times N, from which I should be able to write this as IS equal to root of 2 divided by 3 times IDC. So if when I draw the equivalent circuit of the stator, I should be able to draw it somewhat like this. All I need to do is to give a current of IS, and that IS is in this particular case equal to root of 2 by 3 times IDC. And that is going through RS and XS, which is actually the stator reactance. And I'm going to have XM as the magnetizing reactance here. Now on the other side, I should be able to draw this as R2 dash divided by capital S and X2 dash. Now from this, I should be able to calculate what is the current that is flowing through the rotor, and then we can calculate the torque. So I should be able to write I2 dash is equal to whatever is IS I have got multiplied by the other impedance, which is actually XM whole square divided by R2 dash divided by S the whole square plus X2 dash plus XM the whole square. So what I have done is basically to use the current division rule. So whenever we want the current through the second branch, we have to take the first branch impedance on the top, and we have to take the summation of both these impedances together at the bottom. So I2 dash can be solved for from this. And once I solve for I2 dash, I should be able to calculate the torque. So the torque in this particular case is going to be 3 I2 dash square R2 dash divided by S times omega S, where omega S is the original synchronous speed of this particular induction motor. So DC dynamic braking, because this S is pretty large, it is close to 98% or something like that, we will not get a good amount of torque unless we modify the rotor resistance perceivably. So that can be done only in a wound rotor induction motor. So again, this is really not a very good, proposition as far as the cage induction motor is concerned for braking operation. The last one, what I want to show is regarding zero sequence braking. So let us try to take a look at zero sequence braking. As I mentioned, this particular braking is called zero sequence braking because all three phase windings of the stator are connected either in parallel or in series. So the currents are going to be either in cophasal in either case, and that is the reason why this is generally known as zero sequence breaking, because zero sequence components are always cophasal. So in this particular case, we are not going to be able to really, connect them properly unless we have both the terminals of the stator winding that is available. So if it is star connected, we are going to have, this is the star connected winding. So we should be able to connect this in parallel and connect it to the single phase or DC supply directly. So this is the way we can connect it. Or if we are talking about delta connected stator winding, we can have this as the delta connected stator winding, and we are going to disconnect one of the junctions and connect it to again the AC voltage or DC voltage or AC current or DC current source, somewhat like this. So zero sequence breaking works like this. Now, if you try to look at the normal revolving magnetic field theory and the induction motors winding structure, let us say this is A and this is going to be A dash and this is going to be B and this is going to be B dash and this is going to be C and this is going to be C dash. So if you look at it, if let us say this is A and this is A dash, this is B and this is B dash, and this is C and this is C dash, we are going to have the current entering into A, B and C respectively, and the currents leaving from A dash, B dash and C dash respectively. So we are going to have plus here and minus here, again plus here, minus here, again plus here and minus here. So if originally, if this machine had been wound for 3-pole configuration, now we have plus, minus, plus, minus, plus, minus. This is going to work for 6-pole configuration. So if originally the machine had been for P poles, now it is going to be for 3p poles. So the synchronous speed, if originally the synchronous speed had been omega s, now the synchronous speed is going to be omega s divided by 3. So if you really look at the speed torque characteristics, if let us say originally it was omega s, I would have had the characteristic somewhat like this. This is what is omega s, and this is the axis, speed axis, whereas this is the torque axis. Now the synchronous speed is going to be 1/3 of omega s. So somewhere here it is going to be. So this is going to be omega s divided by 3. So I will have the speed torque characteristic somewhat like this, due to which it is going to have a good amount of braking torque if I compare with the original operating point. So let us say the original operating point is somewhere here. Let me again draw the original operating point. And from the original operating speed, if I try to look at how much is the braking torque that is developed, that is a good amount of braking torque that is being developed. So you would see normally that the zero sequence braking operation gives you a good amount of braking torque, but still it could be in the unstable region of operation. So one more thing is, if the speed comes down to something like omega s divided by 3, if the speed is less than omega s divided by 3, then the machine will again transform itself to motoring operation. So the minimum speed at which the braking operation can take place is omega s divided by 3 as far as the zero sequence braking is concerned. So we have seen all different methods of braking of induction motor in the last two lectures. We'll be working out a few problems corresponding to the braking operation of three-phase induction motor in the next class. Okay.